Alright, so now that we've taken a little detour from transformations to discuss symmetry and whether or not a function is even or odd or neither, we are coming back to learning more types of transformations. So let me just back up for a moment to give you an overview of what we've been doing in this section. In 2.7, this is the beginning, 2.7, we started with transformations of original parent functions that are either stretched, vertically shrinking them, horizontally stretching them, or horizontally shrinking them, like the blue one in this picture that goes with this equation. And then after we talked about stretching and shrinking, we talked about reflections across an axis, and that brought us to discussing symmetry. They're related. Reflections and symmetry are related. And then after talking about symmetry, the next logical thing to discuss was whether even, odd, or neither functions. So we did, again, looking at the types of symmetry that indicate you have an even function or an odd function. All right, now we'll go back to talking about transforming a parent function, because this is a graphing technique that allows us to look at the function and relate it back to our basic parent function and just make some changes for this new transformation. So we're looking at translations now, which is a certain type of transformation. It's one that relocates the original shape. So rather than making it more narrow or more wide or reflecting it upside down or across the y-axis, what we do is we keep the shape basically the same, but we just shift it to a different location on the y-axis, xy plane. So the original parent function here is x squared, which would look like, oops, let's go one higher. Look like this. Okay, the original. And this has something added on to all the y values. So if I did a t-table here and I started off with, let's say, x comma y, or x comma x squared, compared with x comma x squared plus 2, what would that look like? Well, I would have 0 comma 0, and then I would have 0 comma 2. I would have 1 comma 1, and I would have 1 comma 1 plus 2. I would have negative 1 comma 1, and negative 1 comma, negative 1 squared is 1, 1 plus 2 is 3. 2 comma 4, and 2 comma 2 squared is 4 plus 2 is 6. Negative 2 comma 4, and negative 2 comma 6. So every single point in this column has the same x value, but the y value is 2 units greater. So the y value is getting shifted up 2 places. So that means that this f of x equals x squared plus 2 is a vertical translation up 2 units. So my origin got moved up to here. This point gets moved up 2 places. This point gets moved up 2 places. This point gets moved up 2 places. This point up 2 places. And this one goes off the map, so I won't mess with it. Let's see. Here. And here. So it is the same shape. It's not any thinner, it's not any wider, but it's just higher. Is that all I had on that page? Let me double check. Yes. Okay. All right, then, vertical translations. If a function g is defined by taking some basic function we're familiar with and then adding a constant to it, where c is some real number, then for every point xy on the graph of x, there will be a corresponding point x, comma, y plus c. The graph of g will be the same as the graph of f, but translated c units up when c is positive, or absolute value of c units down if c is negative. The graph of g is called a vertical translation of f.